Yo, yo, yo. Yo, Penguin, what's up? Hello, SQF. Welcome back. Hang on, let me set this up here. I'm doing great. Thank you. How about yourself? Have to be a little bit quiet here for a couple of minutes. Awesome. All right, I'll check these out later. Okay. Yeah, Happy New Year. New year, new things to do. So let's see. Yeah, we were last time we were in the middle of changing instructions. So I realized that we could have, instead of having a flat list of instructions, we can actually have like islands of instructions, because when we try to make functions and function bodies, it makes sense to kind of compile them into its own like context. So that's why I came up with a solution of, well, we can have these instruction sets however we want. We don't really need to produce some kind of linked thing in the end. We just need to have these islands and be able to like jump from one island to another. So basically now the instruction counter is actually consists of two variables. So one is which island we're on, and the other one is which local address on that island. And so yeah, so now I'm adapting the code here to that idea. And let's see. Right, so now we have these instruction sets everywhere, and we are using that here. So yeah, so when you add an instruction, we actually have to add a which set is it going to be added to now. So let's see if we can make this work here. So new ref also needs to have the instruction set. There we go. So we'll just add that there. And also I made refs to be shared between threads, because I think it makes sense, because they are like, they don't really thread on each other anyway. And how would threads like communicate if they don't have refs that they can share, like have any memory that they can share? They need some kind of memory that they can share. And so yeah, I just made them kind of global. We'll see how it goes here. All right, so exit. So basically everything now needs like the instruction set. Anything that adds instructions needs to have instruction sets. And of course, when we compile, right, when we compile the kind of the initial thing we should start with one instruction set. Do we actually add that somewhere, or do I have to kind of create it? No. Yeah, I mean, I think, yeah, this is just empty. So if we go back, if we go to the compile thing, we actually need to create an instruction set. So self add instruction set. And that will give us a set kind of identifier or index that we can use. And of course this thing needs to have the set, and everything else needs to have the set as well. So there we go. Yeah, because you do need the set here. And these refs also need instruction sets. So maybe that should always be the first. Well, it doesn't really matter much. There we go. And you also need, wait, set location, right. Now, the location actually could be an instruction, and in that case, it's built in now. So now we have instruction set on all instruction addresses, and then we have a local address, which is either relative, absolute, or label. So labels, actually, I thought before that labels, hey, they could be kind of global, but really it just makes sense to invert it like this. So basically that means that everything needs to have an instruction set, and in all, it just makes sense to have it when you have this structure here. All right, and then we have right, okay, we have to add RC error now here, and do we get that on stream, or let's just import it directly. All right, you also need, well, okay, so I mean we do need an instruction set, because this instruction needs to be added to somewhere, so I'm just gonna have to add it here. Same thing here. And here. Oh my god. Stop it. I pressed some weird Windows combination again. Okay. Right. You need instruction set. People are still not done with the New Year's. Yeah, all of these compile statements need to have instruction sets. Compile return. Oops. Compile expression, of course. And somewhere along the line, like when we're compiling, let's say we're compiling like a function, declaration or something like that, we should also compile the function body in a separate instruction set. And then I guess when we have a reference to the function, if, well, we don't really have that right now, but then we would need to include the instruction set we are talking about. You, of course, also need the instruction set now. Do you actually need... Yeah, I guess for strings, okay. Instructions. Yeah, everything needs this now. Hello, Barshiker. What's up? Wait, you don't actually use it though. Oh no, you do. Okay. Oh, what's this? Expected that, found that. Oh. Sure. Oh yeah, because it's like deinitializing at the same time. Okay. Identifier. So I mean, we could have done it with some kind of... I mean, I guess we could have done it with a context instead. Like we do have IR compiler, so we could have set like, let's just have the instruction, just as we have the instruction counter, I guess. Well, do we actually have that actually? I don't think we have actually. I think the current address was just derived from the current instruction set. Or the current instruction length. Maybe we should have an instruction counter now instead. That would maybe be better. Yeah, okay. Let's just have an instruction counter. Now this would be resolve instruction thing, which we initialize to 0. Alright, so I guess we just undo everything we did. I mean, it would be nice, maybe... Nah, let's just do it like this, yeah. Because this ultimately goes back to an instruction, which should just look at the current instruction set. So basically this would just look at self instruction counter instruction set. Yeah. And then actually also we need to I mean, okay, maybe we don't need a full instruction counter, maybe we just need the instruction set, like current instruction set. Yeah, okay. Yo, Blue. How many medium lead code questions can you solve in 3 hours? I have no idea. Like, yeah, there was a long time since I did any of that stuff. I feel like I'm struggle with some of those because it's like it's not really what you're doing on a day-to-day basis. Like it's like a different kind of coding, I would say. Like you're not always trying to like optimize an algorithm or like trying to find solve these weird puzzles. Like usually I'm not sure, and also I don't really know what medium means. Like I'm not sure what the difficulty level is on that. But I would guess I would be able to complete at least 3, maybe. I mean, I don't know. But yeah, why do companies ask it? I've never had a company who asked that question to me. Usually they ask things that are relevant to their current projects and their like tech stack and all that. Like, what is your experience with the things we are currently doing? And then you answer those questions basically. And it also depends on kind of where you are at your experience level, because if they see that you have like 10 years of experience, of course they're gonna, you know, assume that you know the basics and they don't have to ask, you know, questions about how this language works or something like that. But I have, like, when I first started out, I actually had a company ask some kind of basic language questions, but not really, and to the extent of doing like the I think one thing that I did was I think the FizzBuzz, or was it the FizzBuzz or Fibonacci? It was one of those that I did once on an interview. But then, you know, then even if you get it, like if you get it wrong, let's say, the reason is to, well, if they are like competent, I guess, they would like talk to afterwards. They were like trying to figure out how did you come to this solution. If they don't do that, then it feels very I don't know, shallow, and they don't really know what they're doing basically. Yeah, it's simple, but it's also like maybe you haven't done it in a while. Maybe you've I guess it. I don't know what kind. I don't know what the point is actually. I guess the point is to see if you're able to code at all, basically. I don't know. But you know, they could also just simply ask some questions. And you don't have to go through the stupid test. Like, I don't know what it is about like programming companies that require you to do some silly test. I don't know. Because they could just ask you some questions and then they would quickly find out. Like, if they are competent, if they have like a programmer asking the questions and you answer them and you can kind of have a discussion and all that, then, you know, they would kind of find out where you are. I mean, of course, if you're like completely new, maybe they want to have some kind of reassurance that you've not just studied like answers to questions basically, and you actually can code, I guess, as well. So I guess that might be a reason, maybe, not sure. Right, let's remove that. Okay, so we're adding an instruction set. We also want to set the current set. So actually we could just set it right here and we don't have to pass it around. There we go. So it's context based now instead. And I'm just going to remove that. Whoops. No, wait, current address. No, that's right. So this would be current instruction set. Oh, wait. No, wait, you need the instruction set, but this is going to be the current instruction set. There we go. Okay, still got a lot of issues here. What's the font? Seen before I can recognize it. This is Hask Lug, I think it's called. Man, it's either Hask Lig or Hask Lug. I think it's Hask Lug. Yeah, no, Hask Lig. Because there was like a typo in one of the links, so I never remember now if it's Hasklig or Hasklug, but it's Hasklig. There you go. I sent the link there. All right. It's definitely not practical. You just want to thin out the numbers with competition. Yeah, I guess maybe. I don't know. I don't know how the recruitment process works. I've never been part of that sphere. Like I've been there like once or twice, but it's like I don't know. What's this? Error union? Wait, we don't have errors here. Or do we? Actually, yes, we do. Oh. Oh yeah, these are new statements, right? That's right. They are new statements. All right, so yeah, these were the things we added last time to talk about, like standard in, standard out, standard error as pipes for the foundation of this piping system. So we're basically adding these to the start of the program so that we have refs to these things. Like, yeah, I don't know if grinding lead code will help you with any exam. Well, not in my experience anyway. Not sure, maybe that's not what you asked, but okay. No female apps, right? So this would be init apps, self current instruction set. That's the current address. Yeah, but that makes sense. And this would be, hang on, okay, so this is where it's kind of weird. Like get address actually should now be an resolved instruction address actually, and then we just return the current address. But I wait. No, but we could just do resolve directly here. So, yeah, resolved and init. There we go. All right. Right. So the label. Well, now that's a thing there, the label address. So this is like the address here. We should actually get the local. Oh, shoot. Well, okay, let's actually make one that is the local, I guess. Get local address, which is going to be usize, and then it's basically going to be address self get adder or else return null and then return adder.local address. Okay, so this, so actually we don't want to get the label. Well, we're going to get the local address here. There we go. And same thing down here, I think. Well, actually, address. Well, now we really don't know if this corresponds to the same context. Hang on 1 second. All right. The washing machine is like knocking on the door, so it's, I'm not sure how much came through on that on the stream here, but basic data structure help me program lead code does not. Yeah, lead code does. I mean, those kinds of problems doesn't help you, as you say, in actual real world problems. Like it's more like programming puzzles. It's more like a fun puzzle thing. But actual problems that you encounter looks basically nothing like those problems, unless I mean unless you're dealing with super constrained scenarios, but that's just not the case anymore. Like maybe that was useful long ago when computers was super slow, but you know, yeah, because that's what that reminds you of. You have to kind of think like solving some weird string puzzle. Maybe that was relevant long ago or something like that. I don't know. But it can be fun sometimes to do those things. But I would rather build things than do those puzzles, because you don't really, I mean, it doesn't really like get you anything that you can use. Basically, it's like, it's very contrived examples that you're trying to take, or contrived problems that you're trying to solve. It's not, the solutions are not useful, at least from what I can tell. Like, most of those are not useful for like real world problems. Local constant errors function. Okay. Yeah, okay. Fine. Alright, so you are set label. So yeah, so here's the issue. The label is actually now in a context, so we have to make sure that this label is only gonna be used in the same context, actually. So I guess we just have to make sure that that is the case. Because we have the key. Maybe we should just get the key here, actually. No, because we need to use it as an actual address as well. I mean, yeah, let's just do local adder dot label, because that's where it lives now. And same thing here. So the thing that could change here is, like, when we compile any expression, the context could change potentially. Like, the instruction set could change, but I think it's like the responsibility of the compilation of a certain place that if you're changing the instruction set, you have to set it back once you're done. So I think we could assume that we're always working in our own set. Yeah, that makes sense. Okay, that was everything except for this oops, I should have done f reference trace. So this is happening in the evaluator 49, run instruction 132. Here. Right, so you need to be F now. Okay. There we go. All right, now we're back, and let's check out. Oh yeah, these are all the things we're doing now when we're trying to set up a pipeline. But we don't really have a way to compile pipelines. Well, I mean, I think we allow them to be here, but we don't. Oh, write failed. Interesting. So that happened from where? Maybe. If not LeetCode, what do you recommend to get into programming for an IRL scenarios? I mean, just build a project that does something. That's it. Like, you can build anything that you can, or well, I should say that, like, yeah, you can build anything that you come up with, and if the kind of ambition level matches the experience, basically. I mean, the thing is, like, if you want to, it kind of depends. Like, do you want to build a large project? It's gonna take a while, you know. I would recommend, like, trying to figure out like smaller projects that does something that is challenging in its own way, but it could be a real application. It could be a part of a real application. Like, go out and look at what are real applications actually doing, and try to mimic that. Try to pick out like one part of a real application, let's say, and just one simple thing that it's doing, and try to solve that issue by yourself, or come up with your own idea. Like, come up with your own app idea or something and try to do that, basically. And treat it as an experiment. Treat it as a learning experience. Do not treat it as your life depends on actually making this work. Just treat it as a learning experience, and you can do it over and over, and you will gain experience and you will gain skill over time by doing that, trying to solve like real world issues. Hello Polaris, welcome back. Yeah, that's all. Like, build projects. That's how you learn programming, and actually potentially also have something to show when you search jobs. I know it doesn't. Also, it doesn't have to be like a huge project or anything. It's better if it's small. It's like it's as tiny as you can think of. And then, you know, it's up to you if you wanna add features or start another project, or yeah, like redo the same thing, but next time you've learned that you've learned that, okay, if I do this, that's a bad choice because of this and that, or like that's how you learn. Like, you learn that, well, this pattern fits here because of that and that, or this pattern fits here because of that and that, and then you kind of build up your knowledge that way. Although I'm like constantly trying new patterns all the time. Like, I'm constantly, and that could be also be a bad thing if you actually want a project that's like long lived. I don't know. Sometimes also it's like the projects are, I guess, there's no silver bullet or anything. You just have to tread through building, or like if you have a large project, oftentimes those become like more and more unwieldy over time. Like in the start of a project, everything feels nice, and it's like, yeah, I made this all a plan to make this and that, and then I start to work on it, and then you came to the conclusion that, hey, we need to change this because of that, and you have to rebuild some stuff, or but the velocity at the start is always faster than at the end, of course. It's kind of self-explanatory, but it's like you can really feel it when you're in it, so to speak. Okay. What are we doing here? Yeah, I'm gonna see, like, where do we have write fail? I mean, we have write fail basically everywhere, because that is a standard error when you can't write to something. So I'm gonna see, but if we get an issue here, what happens? It bubbles up somewhere. We have the step function that also bubbles up the error. we have the runner, which we just try here. Okay, so and then this would bubble up over here where we try to run the IR. So, and then this also bubbles up at somewhere over here, which then bubbles up as well. So we don't really have a stack trace here to see where things went wrong, but we could add something at least. We could like, I guess when we step here, we could say like if something went wrong, we can catch it. Well, we don't need to switch on it, but we can catch it. And then we can say let's just log an error actually. Let's do error evaluating, and then we would have where's the I thought we have like a log thing that was nice. Maybe it's private log. No. I think we want to have this log, even though it's like, okay, well anyway, so we have the evaluator step, so we could get like the evaluator, we could get the context, and we have like, you know, we have the instruction counter, get, well, we could get the thread context. Wait, yeah. Get current thread. And then we could get the current instruction. Which I guess could be null, but right, so I guess if we have it, we can say, well, it should also have a source, which I guess also can be optional, but god damn it. But if we have a source, that now means that we can get the span, and we can get the file, and we can say error evaluating, and this is the file name, and then we have like line. Actually, do you have a format? No. Maybe we should just add a format function to the thing. And then we have like start, line, and column. Of course, it could be global. If it's global, then, Well, actually, it doesn't really make sense. It doesn't really matter. Actually, let's just get the span like this. All right. So we have the line and the column. All right. Okay. If we don't have the source, and also let's do error. We don't have the source, error evaluating, and then we'll format the instruction address. Oh shit. So actually, yeah. So this would be the address is gonna be current thread address. Yeah, we'll format the address. And here we could potentially also get the source line, the source code line here, but or just the expression. Actually, we could just get the expression. Okay, but I want to do a super fancy thing right now. I'll just do this thing here. We'll return the error at the end. If we don't have an instruction, I guess we just say if error yeah, then we don't say anything, I guess. Column. Oh. Typo. Thank you. All right. Okay, so let's go back and try this now. So what do we see? Okay, we don't get anything. Oh, I think it's because we don't run it with verb. No, wait, we should have gotten it because it was ran with something else. Okay, so if we run it with verbose, we actually get instructions here, but then write failed here. So after we create these refs, we should have these set instructions, but those apparently does not work correctly. So okay. Here. So I guess it fails here, maybe. Not sure. And we don't have the tracing we do in other places. I would ask AI to fix that, but no, I don't want to spend time on that right now. But yeah, okay, so we get a write error. That, where would that happen though? Because these things should then be. No, wait, we should have compiled the whole thing because we are actually, yeah, we have compiled everything. It's just when we try to write this set, we get an error. Maybe it's because it's trying to format the stream or something. I'm not sure. Yeah, maybe that's it. Like we're setting to a value. We have the format function somewhere here, and if we have a stream, we just write stream out, so we don't really, that shouldn't really be a problem. But then again, that I don't think that's, maybe that's not the issue, because the hang on. Here we go. So here's the verbose stuff, right? Instructions, and then we loop through the instructions. We log, but we only log it for verbose, so it's kind of weird that it would be an issue here. Log instructions actually doesn't, wait, the writer to a message buffer. Okay, maybe this is where it fails. Print I is a U size. Instructions. No, so it came to the like the fourth instruction. And then fails. So is it happening in here? Is anything happening in here? We have the fixed buffer for 1024 length. And we don't even see this here. Oh yeah, we don't see it because we haven't written it out to stand it out yet. This only writes to the message buffer. Okay, so we print this here. We will loop through this label counter, right? That's right, because we have a bunch of labels. And this might be the address where the label is actually in. However, these labels are actually wrong. But okay, that's not the issue, I don't think. And then we're trying to format the instruction. Maybe that's where things go wrong. I don't know. We're just formatting the type and the source. The source is just the expression and statement. The type can be, well, I think it's like set. And then we just format location and value. It just doesn't feel like this should be an issue. So it feels like I'm barking up the wrong tree here. Maybe it's this, like we're trying to format this value here. No, that's a string. No, the pipe, yeah, that's right. The pipe is then format. Do we even have a format function on you? No. So how does that work? No, yeah, it's this format, right? And then we just write this. Okay. No, actually, the pipe. Oh, the pipe just does this. Oh, we're trying to read from it. No, I don't know. Because this is like, it's a... No, it doesn't have a reader. No, that's not how it works anyway. So we try to print that as something that would be like a compiler error, I would assume, because this T could be this reader writer stream thing. And okay, I'm just gonna add a pipe here and see if that issue is fixed.
Okay, it seems to be better. Okay. Right, so here you can see it tried to write this pipe out. Maybe I should actually say pipe instead of stream. But yeah, we do get some errors. Pipe null. What is that? And then we have a bunch of stuff happening here. And here's the actual evaluation here. And we call some stuff. And we get file not found. Oh, is it trying to call get line? Right. Okay, well that makes sense now. So we're getting a file not found. That is actually what we would expect here, because get line is not a thing. So I will just, this was just an example of showing what this would be here. But let's remove that. And there we go. Now we actually get this here. But we don't get anything here because this doesn't actually compile to anything. If we look at this, this is line 16, so we don't actually see this line anywhere in the code. Actually, the first, oh, the null is the like the line of code, right? So the first line of code is actually 31 that we reference from the which is down here. So this is the first line of code that's actually like compiled to anything, because this is a pipeline and we haven't done that yet. So okay, which we are currently trying to do. But okay, so now we've got basically back to functioning state here. So let's go back to the dreaded compilation of the pipelines. Compile pipeline. All right. It feels like I'm putting this off more and more, but I feel like I'm kind of trying to build towards support for having pipelines rather than trying to put it off, though, because there's a bunch of stuff that needs to work. So if we go here and, well, for one, we see that here we have like the outer context. This is like, you know, standard in, standard out, standarder that we are setting up here, kind of like magical refs that is automatically wired up to the outer context. And let's see if I remember now how I wanted this to work. So basically here, since we are in a bind context, we wanted to create a ref and create a pipe. And then well, okay, this example doesn't really match what's happening here. Actually, this example is basically just an example how you create a pipe. But then what you can do with it. So we basically create a pipe at ref 3 and we forward the output of 3 to the input of 1, which is standard out. So we're basically connecting those pipes. And then we have standard in, which is 0, and we connect that to this pipe over here, which is 3. The thing is, though, these pipes only have like one output and one input. So you couldn't say, for example, if you want to create another one, 4, and then you connect this also to standard out. But you could do that, I guess. You could do that because... No, it depends on how you connect it. This is where I made this so convoluted. These pipes are very... They have like different ways to connect. Depending on like if you want to close the executable. But basically, if we want to say traditionally, if we want to say like, okay, well, we're connecting this to standard out. Well, since these pipes only have like one input and one output, this doesn't work. Now this has kind of taken over this. So now 4 is from the only thing that goes to standard out right now. Thank you, piano. And then here we have, let's say we want to also forward standard in to 4 as well, like in parallel, let's say. That doesn't work either because 0, like the pipes only have one destination. So this is basically changing the destination from 3 to 4. It's like redirecting to one thing. So either we could build in multi-source, multi-destination support on these ones to make them be able to do that, which could make sense. But it also feels like they are becoming some kind of monster as well. So this is a ref address. Or a ref identifier. So it's basically double at. So the language that I'm looking at, that you're looking at here, is the intermediate representation language. So it's kind of like in between assembly language and the runic language that I'm building. So I'm compiling down the runic language into this language here, which I'm basically making up on the spot. And what's happening here is we create a ref here. So this is basically creating a location in memory to keep a value. And the value can be anything, let's say. But this creates a location in memory, and then at 0 refers to that reference basically. So if you're setting this to this, the first ref will be set to this value here. Yeah, I think it's interesting because like in some ways the assembly style is like easier to think about in some regards, because it's so simple, but then it's also like some concepts need to be translated into the language in a certain way. But I find it really interesting and fun as well. But it's super simple. Like it's just this is the first instruction, second instruction, third instruction. You have an instruction counter that just counts down, and when you go down the line, just like normal programming, although this is even easier because you don't have to deal with blocks or anything like that. This is just a simple list of instructions and just execute one after the other. Forward 3, 1 forwards of data written to stream 3 into stream 1. Yes, that's the idea. So basically we're connecting the stream 3 into this, or pipe 3 into pipe 1. I'm interchangeably calling this pipes. I'm using pipes, but the actual type in what I made it is named this reader writer stream. The question is if this is an actual issue though, that they can't have multiple inputs and outputs. I mean, we could build that support for it, but it's like, okay, maybe I should wait with that until we actually have this issue. Because what's gonna happen here this isn't gonna connect. So let's say we do. I'm gonna not think about this one. Let's go down to this example here, where we have this pipeline. I'm gonna remove all this down here. So we have this pipeline here, and this is okay. So this is still the same kind of example here. Oops, F2. So let's imagine this is the only thing that's happening here. So, and then we push this argument. So we're basically pushing this thing as a kind of like a call executable in context, and we call it, which means that we pop this value and we like use this argv to call the thing. Now the thing though is that this needs to output into cat here, so we can't just call it, because that's just gonna call will basically try to wire up against, well, okay, maybe when we call something, maybe actually when we, this context could have, you know, standard out, oops, be something. So this could be like, you know, standard out is 1, standard in is 0, standard error is 2. So that would be the normal thing. However, we could add that to the context. That's going to be pretty easy actually. But now is the question, how do we wire this up? How do we create this stuff? So we need another ref before here, which is going to be a new pipe, which is going to be representing this here. So then simply standard in is just standard in, so that's fine. Standard out is actually going to pipe into 3 now. So that's the standard out. Standard error, I mean, I guess we need a standard error as well, so we'll just create another one for standard error as well. And this will be 4. And then we also forward 3 to 1, and we forward 4 to 2. Actually, you know what? We don't really need it as separate for standard. We could just forward directly to 2 here. Yeah, unless there's captures or redirections, then we need to do something different. But for right now, this is gonna have to do. Okay, I represents the command echo hello cat by creating a pipe stream that forwards echo samples to cat booms. Yes. So this is kind of, we're breaking down the problem into these instructions here. Does command T has multiple out streams? I think that's how it works. I've never really used it myself, but from what I've seen, it can you supply a bunch of like file handles or file names or whatever, and it would copy the output into each one. I think that's how it works. Although, as I said, I've never used it myself, but yeah. But that works like from within the command, like in the executable T. I think it's an executable. Yeah. Okay. So we don't need this, but we create these things. Standard errors, like by default, not like piped anywhere. It just pipes to the default. However, okay, so now this is piped in there, and then cat standard in is actually going to be the 3 now, and then standard out is the normal standard out, because that's the last thing. And there we go. And then at the end, we actually need to wait for... I mean, actually, we need to wait for cat here. And what wait is gonna do is, actually, we're gonna wait for this pipe. And what that's gonna do is it's gonna forward it. No, wait. How is this gonna work? So forward, actually, this is interesting, actually, because we can make an action, we can make an instruction that actually streams the data through as well. Yeah, standard in is 3, so this would take the output from 3 into cat and then output to the normal standard out. But now the issue remains that we need to do this in a streaming manner. So all of the, like this pipe, I mean, now we only have 2 things. Actually, we have one more. It's kind of like this. It's kind of like we have this that goes to standard out, which is this pipe, this one here. So basically, I mean, it's kind of like anytime we have a pipe, we just constantly want to stream it through. So every pipe that's created, we actually want to create kind of like we want to create a thread, a virtual thread that would stream that data through. Which was the pipe threads that I was talking about a couple of streams ago. But now we could maybe make these into instructions. Forward 3 to 1 is useless. No, we'd have to wait. No, we have to connect so the oh wait, yeah, you're right. You're right. I don't know what I was thinking there. Yeah, because cat is wired up to out, and so this would be the input to this, and this would be the output from this. Yeah. So it's fully connected basically. Yeah. Okay. Yeah, good catch. Yeah. But now the issue remains that these need to be kind of they need to be maintained. Basically, they need to be churned through and they need to close and all that, which has to happen asynchronously. So I think for everything that we create here, every reader-writer stream, I mean, we could cheat and put them in some list somewhere and just loop through those and forward it. We could do that, maybe. Hang on. Did we have a wait here? So we have a wait for like thread, but we don't really have a wait for a pipe right now. So if we go to context, so how this works is that we have like pipe threads. Now these threads are meant to churn through the pipes. We have 1 thread per pipe, and it's 1 thread per pipe, 1 pipe per no. Yeah, 1 thread per pipe. I have a question. Is the data inside 3 being deleted after Echo finishes job? So the data is basically... So what's happening here with these reader-writer streams is that they can buffer data. So if let's say echo outputs to reader writer stream, it's gonna buffer some data, but only if we don't have a destination. If we have a destination hooked up, which is this cat here, later. So this would be later hooked up here and called, which would start to read from this. So this would connect the destination of this pipe to be cat standard in. And in that instance, we might have gotten some data from hello already, which would have been buffered, or which would be buffered here. But as soon as cat is connected over here, that buffer data will be outputted into cat standard in directly as soon as it's connected. And then whenever data is flowing from echo into this pipe, we also forward that data directly into cat. So all the data is just, it disappears immediately, basically. Like there's no backing up of the data as long as the pipe is connected somewhere. If the pipe is not connected, the data is like buffered up with using a heap allocator. So it could potentially hold, you know, a lot of data. And then, you know, in a pipeline like this, we would wait until this source is depleted, and then the pipe kind of closes the source, and it also closes the destination end, which would close the standard in of cat. But then we also have standard out, which might not be closed yet. So it might have more data coming out from standard out. And once that is closed, then we also, or depleted, the stream is ended there, we close standard out of cat, which makes cat exit cleanly. But we also have to kind of wait for the process. So basically that's done through the reader writer stream. The reader writer stream actually handles closing the process as well if both ends are closed. Replace hello in an echo section with a very large text. Well, yeah, that is a different issue. So that is like, okay, yeah, because yeah, this hello is actually gonna be stored in a read-only. Since it's a constant, it's stored in a read-only section in the kind of the program. So that would be stored in some read-only place, and it would be stored in memory. Like when we interpret it, it's stored in memory, and will be just, yeah, I guess it will be just called, given to the operating system, you know. Yeah, if hello, and okay, I see what you're getting at. So and then echo would take that and try to echo it to cat, right? Is that what you're talking about? Yeah. So I mean, if this is a constant string, then it's stored. It's like stored in memory for the duration of the program. But if we, let's say we try to read a file or something that is super large, then because this is a stream, it would just stream through. It wouldn't like keep the whole file in memory. It would just stream it from start to end into cat, which would just stream it out to the terminal. But yeah, if this was a super large like constant, then that might have some kind of limit to it somewhere. But yeah, I mean, it's stored in, I think, on the heap or something. I'm not sure. Yeah, it's stored on the heap because it's a dynamic. The read-only data is a dynamic array of bytes. If the screen starts filling up instantly. It's operating in parallel. Well, yeah, yeah, okay. So this constant is stored on the heap when in the interpreter. If the screen starts filling up instantly, it's operating in parallel. If it waits for a while and then prints everything instantly, it's operating in sequential buffered mode. Yeah. So that's the whole point of this reader-writer streams and all that. Like the whole point, and I'm trying to solve, is that we want this to happen in a streaming manner, and that's why we have these reader-writer streams, so that you read in a chunk of data and output a chunk of data to cat, and then you go, let's say we have another pipe, for some reason we have 2 cats. Now this is a bit different, so now we actually have, maybe here we have another ref, and we call cat again, but now we have another ref, and the standard out goes into 3. We have this standard in goes from 3 to 4, and you read from 4 to 1. So this would be what's gonna happen here. Yeah. And then what's gonna happen is that, so this is not the full story. That's what I'm trying to also think about here. This is not the full story, because we need to also process these streams. They don't forward things by themselves. We need to actually call a function for them to read from echo standard out and forward it into cat standard in. So we actually need to process these streams somewhere, and that's where the threads coming. That's where these the threads come in. So we go through all the streams where we stream them through, and I'm contemplating whether or not to just add a stream instruction for those things, that we could like spawn a thread, like we create a function for each pipe that we have, because we know all the pipes. We could create a function that whose job is to churn through, let's say, ref number 3, ref number 0, ref number 1, and so on. Or we could also have a, well, I mean, we could just have a, we could have a loop that goes through all the pipes, because we should know like all the pipes. We could just look at the refs and look what's in there and just loop through them, and because they are shared between all threads as well. So we could just have like one step at the end where we just forward every pipe. Yeah, let's actually try that. And then I don't really think we need multiple inputs and outputs, because only one of these, it's like, if it's when we get like redirections, let's say this goes out, let's say we do like this, like 2 is piped into 1. I'm not sure if this is the correct syntax here, but let's say that 2 is piped into 1. That would mean that whatever this, now it probably doesn't do any errors here, but let's say it did. Now actually 1 should be getting both from this output and from the end here. So now we have 2 outputs into the same destination. So that's a thing. So I think we actually do need to at least have multiple inputs. Maybe not multiple destinations, but we need multiple inputs to these. Yeah. Close 3 is missing. Yeah, well, as I said, this is like not the full story here. This is just setting up this pipeline. Once this is done, we also need to wait for something, because if we, so every time we, so this is like asynchronous call. It's like we're calling this, but we still keep going. Like otherwise we would have been blocked here. So this is kind of like an asynchronous execution of this. So we spawn up the process, it's gonna start to output stuff, but then we continue instructions here. And this is asynchronous, so we go down here. Now here, since we're at the end of the statement here, we have to wait. So we're gonna do some kind of wait here. Now what do we actually wait for? I think we wait for, I mean, it's gonna be the last thing, or we wait, or if we say that we wait for some thread, we're waiting for, we could spawn a whole thread for the whole thing. That's also what I was thinking, like maybe we could make threads in as an instruction as well, like fork. Yeah, actually, no, what the hell? I actually did have fork as an instruction now. That's right. Which has a destination. Yes. Okay, well that was one of the things that I did last time. Right. So actually, and since the threads have kind of their own context, like the standard out, standard in, or they could have their own context. Yeah, it's kind of, it's like another way to do it, basically. And then this could maybe be blocking, maybe maybe not. No, because yeah. Yeah, it's either wait on 4 or we wait on, like we somehow get the process ID out here and we wait for that thread. Like we're trying to wait for a thread. So basically here, let's say we will fork. So, okay, another thing that I introduced now is instruction sets or islands of instructions. So this could be like this is like one instruction island. However, we can also make this an instruction island. So let's say this is like this is actually like set 1. So at first you have like set 0. So basically you could think of this as separate instructions, instruction lists, and they can't really go to each other unless you do a jump. Like at the end of this, you won't be able to like continue down here. It's gonna be the end of this instruction set. Now what you could do then is you could say like here, let's say we want to fork into set 1, let's say, and that would like start over here, let's say. So that would spawn a thread over here, which spawns the thing. But we do want to create this ref though, which that is supposed to be in. But I had an idea like that maybe standard out, standard in could also be part of fork. So we would kind of like set standard out, standard in to be in here. So this would be like standard out. Let's say standard in is 0, standard out is 3, standard error is 2. Right? So that would be like in the context of the thread. Hello, buffer. And some number that I was trying to decipher there, but I give up. I think wait at 1 is perfect. No, okay, well, that's that. If the last cat is finished, that means data is passed through the entire pipeline. Yeah, so wait 1 or added 1 would actually would actually wait for the standard out of the main program to close, which shouldn't happen. It shouldn't happen until we're at the end of the program. So we could wait, but we could try to capture the process ID of the last cat, and we could wait on that. That's what I was thinking. It's an Intel boot signature. Oh. Okay, so this is set 1. So here we spawn echo. Hello. Now let's say that we don't actually do this. Okay, this is another way to do it. So we fork over here, and this would call that, and then we wait for the process in the thread, let's just say. Which also should but the problem is we also need to churn through this thing here. So we kind of need to forward or stream ref. How would we actually access these though? That's the issue as well. BIOS load first sector of hard disk into RAM and see that magic number. Does it still work with all the fancy, like, because it feels like an old schoolish thing. Okay. No, okay. So because I was thinking like, hey, this could be some kind of magical behind the scenes thing, and then you would actually stream. Let's say we just stream. We read from standard in to standard out. Right. No. Wait. No. Well, I mean, yeah. But also no. No. We stream standard out. Actually, stream standard. Yeah, this is the only thing we need. Because, the stream function, or actually it's called forward in the code. But it would take a pipe, read from the destination and output to the, or read from the source and output to the destination. And I guess if we have this stream, either we have to kind of do a loop here to check if the stream's closed or something. I think actually what we want to do is say that, hey, this instruction would then, in that case, it would just consume, it would be a loop until it's done. So this would kind of wait for that to be done. We could also call it wait, which would have the forwarding, but stream would kind of it would say that, or it would imply with the name that it's also forwarding the stream. It's actually streaming the thing through. So then we wouldn't call this over here, but then we do another pipe here, which we then have set number 2, and yeah, it's the same thing. We call it with stream ref1, which now would refer to 4. Wait, yeah, standard in is 3, standard out is 4. But now we also need to read. No, that goes in there. I think there's a deadlock. Really? Welcome back, Borrow Checker. It works. UEFI's new standard nowadays. Linux still follows. Okay, cool. Yeah, I know about the UEFI, but didn't know too much about like BIOS stuff before. Is this good though? We'll create like one thing, because this would be one way of like in the instructions actually being able to stream through these things in threads. Yeah, so the way that I was thinking that this would work now is that we actually we do these forks instead. Actually, this could be fork set to both of them, because this calls cat in the same way. Although that would be like a compiler optimization. It would probably be more like this, actually. And then this would be just copied right now. So the way that it works, the way that I'm setting it up now, because none of this is like implemented. But the way that I'm setting it up now is that you could, when you fork something, you could also supply for that thread only a standard in, a standard out, and standard pipes. So instead of having it in the call, we have it in the fork. Because the thing, and I think that's better actually, because the forks are more generic. These are very specific to processes. These are only used for processes. So this is more generic, and we need it to be more generic when we're gonna work with blocks and functions. So I think this is probably the way we want to go. So we set up a new thread which goes into this instruction set here. Yeah, it's probably something wrong here, but I'm just trying to figure out the process here. So okay, well let's figure it out. So this is 3, it reads from, so the first echo here reads from standard in, pushes out to this pipe. Then we have another one here. This is the first cat. It reads from echo, outputs to, oh yeah, so this would be 1, right? And this would be 4. There we go. Yeah, this is standard error. So it always goes to 2 unless you redirect it, but we don't have that right now. And then, so this would be standard in, standard out, standard error. The first one reads from standard in. The real one, it outputs to standard, or it outputs to this pipe, which goes into cat, standard in. And then standard out from cat goes into the next cat, standard in. And then the last cat's standard out goes into the actual standard out. And then in these things, in these islands, we now have these threads that we fork, and we call the things and we stream them through, which is a blocking instruction that would block until that pipe is done, the standard out, which would forward, for this one for example, it's gonna stream this into standard in of cat, and for the next one it's gonna stream 4 into standard in of the next cat, and then this last one is gonna stream the output of cat into standard. Actually, this would be like a duplication of streaming, because we probably, we don't wanna, well, man, okay, maybe, yeah, no problem, piano. You know, these kind of things is easy to mess up. I mean, I messed up already a bunch of times, so it's like, it's when you're working with these numbers and stuff, it's like easy to mess up these things. But yeah, so we could do it like this, and the good thing here is that we could put whatever in here. We could put a function call, we could put any kind of expression here. It doesn't have to be a process call. It could be anything, and we could set up a bunch of streams or do whatever. Now the problem remains here. Wait, we could also call, so basically we want to, so basically where do we get this, the result of this fork, or the kind of the thread ID of this fork? So we need to be able to get some result back from this instruction. Now I did have like registers in the first iteration of this, where you could store things like that, for example. But I think I removed that because I didn't. I ended up not needing them. But maybe it's necessary if we want to actually get some result back from an instruction. Actually, we could also have a special, I mean, yeah, it would be kind of like a register, which you kind of had like last spawned thread ID or something. So then this would be like wait for the last, maybe it's like baked into the instruction as well. Let's just wait for the last fork that you've spawned, maybe. I think it should be fork set 1 032 fork set 2 342 fork set 3 412. Yeah, that's what I have. 3 forks, one below the other. Oh, you mean like this? Or because this doesn't actually matter that much. I mean, it doesn't really matter, because I was just thinking of how the compiler would probably output this, perhaps. Maybe not actually. Maybe this is how we actually were gonna do it. But anyway, yeah, it doesn't really matter because the 4 is not referenced before here anyway, so it's not referenced here, so we don't really need it right here. But yeah, well, whatever. It doesn't matter that much. Yeah. So anyway, yeah, this could work. The problem here also is that 1 is kind of referencing ref 1, where we probably want a special case, like a special reference to standard out, standard in, standard actually. Like I was thinking that we could have introduced a new address type, which is file handles, but then I realized, well, we could just use refs. I mean, they could be any value, and now they happen to be read-write streams. Yeah. Yeah, this is an issue here. Like, the issue is, how would we know that we're talking about this thing? Do we need a new kind of address is the issue, because this would still refer to this number, to this ref over here, unless we make refs local to threads. But that does I don't know. There's some, I don't know, it feels wrong somehow. Because if we make them local to refs, we wouldn't really, or threads, we wouldn't really know which ref we're talking about. They are global, like the address of the refs are global. And there's no like magic instruction to set this up to actual standard outs. We could have that. Maybe we could actually have a instruction like forward. No, not forward. We could have a special instruction for forward standard in, forward standard out. We could maybe have special instructions, because then this would be set up in each thing here, except here no, what the hell? Wait, how did I think about this? Yeah, the problem is though that it's like, you know what? Maybe we could push actually instead of. No, but the threads have different stacks. Okay, actually, you know what? The fork instruction receives these, and what that's gonna do is it's gonna create a thread and then push these to the stack. So we could now talk about the stack. Let's see, value address. No, where map address? No. Where's the thing? No. God damn it. From address. No, location. Yeah, location. It's called location. There we go. So we have the stack location, which is called S. So S0 would refer to the first thing on the well, not call, but stream S1, which would be this so we would like we wouldn't see any push. We wouldn't see any push instructions. The fork instruction would push these automatically, and then we can refer to the stack, to the arguments that comes from the fork. Yeah. What about add another parameter that's a bit masked to ignore standard out parameter forward or use it? Yeah, that could be a cool. Yeah, that's a good idea. Let's see. I'm just trying to figure out like the basic structure to like the most basic case of a pipeline here. Although I do have like an unnecessary step, which is the third, but it's just I think 3 is a good base to start to figure out. But yeah, let's say that the fork instruction actually pushes these onto the stack. So then the first item on the stack would be standard in, the second item would be standard out, the third would be standard error. So we don't actually need to push or pop those ourselves, but we could assume that it exists here. So we just say that, hey, the first item or the index 1, which is the second item, would be standard out. So we stream, so we take that pipe and we stream it. And actually, you know what? The last one, we don't actually stream that. Or wait. No, we have to stream. No, we have to stream it, but okay, anyway. Yeah, so it would be stack 1 instead of ref 1. There we go. Now it's like local to the threads. There we go. So that means if we go to instruction fork, we would have a destination, and then we would have standard in, which should be a location, standard out, standard error. So we evaluate this. This would create. There's a spawner thread. It would take, get this instruction address. It would push these things onto the stack. We can then refer to them here because these islands are basically created specifically for this purpose to call this thing here, or yeah, to execute this pipe here. The thing that I'm thinking about now is this part here. So this is the standard out pipe, which should be kind of like always processed all the time. So it's not really the job of the last set here to actually stream that. Because that should happen somewhere else. But we do still need to wait for this process here. So I think push RB low standard sounds great. Yeah, you want to go back to the first thing Well, I've said like the reason why I don't want to do that is because I do want to have these threads, because we don't always want to have a process execution here, or like an executable call here. We could just want to, let's say we have a function called, I don't know, process hello, or convention process hello. Now this is not a process. This is a, well, it has the name process, but this is a function that would take this standard in and output to cat now. So we wouldn't always want to have a process here. So now this would actually not be cat here. This would be like, I don't know, we don't really have a way to do this here, but this would be like yeah, just, you know, it would be something that would call this call function process hello, you know, which would then, but how would we know? Okay, maybe stack one is always gonna be standard error, because the thing is we need a consistent way to refer to the standard out, standard in, standard error. We need a consistent way. So maybe the stack is the answer actually, because that is thread local, and it should be good. So actually, instead of making refs here, we actually push these things instead. We push this, and then you're ref 0 now, so it's gonna be a little bit confusing here, but this would be stack 0. Oops, did I see? Stack 0, stack 2. It also kind of look like standard, you know, standard in, standard. No, this is not. This is ref 0, ref 1, and this is stack 1. There we go. All right, there we go. You think stream S1 is wrong? What do you mean wrong? What do you mean? Wrong in what sense? Like, is it the wrong term, like stream, or is it the wrong, like, instruction? What would you replace it with? I mean, I think call should actually be for functions. Call should be for functions, and then this would be like execute or something. Execute, executable, run. I don't know. Exec maybe. Exec is probably a better name. And then this would be call, and then some kind of function here. Stream S1 is wrong because it's blocking. Well, what do you mean? Because these should be blocking here, because the fork will be blocking. It doesn't matter because this is a fork, so we would, you know, this isn't the function call. It would create a thread over here which would go through, but in the meantime we also create a thread here which would do this, and then we create a thread here which would start this. And then we're down here, and now we wait for this fork to be done. And in the meantime, this would have gotten down here, and now it's waiting for this pipe to churn through. And we're waiting for this. We're actually waiting for this process to finish. And that's fine. Here I could argue maybe, I'm not sure. But for an executable, this should be the way to do it. And it doesn't matter if it's blocking, because it's in its own thread. So the main thread could still keep going, even though this thread is blocked now. Or I'm not sure what if like what issue we're pointing out. Running stream S1 command means you're trying to interfere from outside with data flow. System already manages automatically, I think. Yeah, that could happen here. So, well, what you have to also keep in mind is the S1 is thread local. So this S1 is not the same as this S1 and this S1. So that's one thing. The other thing is here, this is actually is, to your point there, is that this S1 refers to the actual standard out, which we should be processing anyway somewhere. That should have like its own thread somewhere, which it's always processing that. So but it also means, yeah, it means basically that we just cut off this last one. So this last one we just don't. However, now we need to kind of know how to, now we need to kind of, we need to have some other instruction to actually wait, either call this synchronously. Maybe we call this synchronously. We have a sync flag here maybe, or we have some other wait instruction or something. I'm not sure. Maybe we'll add like a sync flag on the exec instruction to have it synchronous. But yeah, because the last one actually we don't need to process the stream because that should happen somewhere else. We could actually have like a set, I don't know, question mark, and this would just stream S1 somewhere. And we fork that like immediately, like we fork it somewhere, and the same for S2 and that. So so yeah, it also means, well, we need a couple of things for this to work. I'm just trying to go through everything we need for this. So this would not be streamed, but then we also need, potentially in the future, we need to, because if you want to be able to have multiple outputs to stand it out, we need to have multiple inputs as well. But that's maybe not MVP right now. And then we need this, so we need this wait instruction. Actually, we could just add that right now. Do we have wait already? So we have a wait, pipe or process. Wait here is a location, so it could potentially be anything actually, but we don't really have a way to refer to the fork here. So and this is not really implemented right now anyway, so it's like, yeah, so we could change it. This could just be wait for the last spawned thread to close. And then we can remove this. All right. Okay. Now this part I'm not too sure about. Like if we need to stream here, the function itself could then also do like other stuff. Like it could spawn processes to echo and all that. But that would, in like theory, it would just wire up correctly, and yeah. And you know, the thing is also like we need to support background processes, so you could potentially have, that's also like you have multiple sources as well in the case of background processes, because you could call like, you know, echo hello in a background process, and we would potentially be here before this is done. I mean, probably not in this case, but so this would now change the whole thing. So this would like call this in a separate thread, of course, I mean, I guess that's it. It just spawns a thread and then does the thing in that thread. I guess that's all we need to do. I don't know, maybe not. And in the end, we need to wait for everything, but I think we're doing that anyway now. But yeah, this would just spawn it in a thread and then wait for it. Although you would want to be able to bind to it, so you wanna, you know, grab the process ID or something there, or not the process, but the thread handle. So S0 now is standard in. I'm gonna add this kind of comments in the comment here. We don't have comments in the IR because we don't have like, there's no parser or anything for the IR. This is purely in like in zig data structures, but this would be standard out and this would be standard. So, and it's also like S0, S1 and S2. So S0 refers to this, so S0 always refers, which is the first item on the stack. It always refers to standard in. S1 always refers to standard out. S2 always refers to standard er. However, it could, like in a thread context, it could have changed to some other pipe. But we still say S0 for standard in, S1 to standard out, S2 to standard er. It just depends on the context where you're in. So in this context here, S1 actually refers to this here, the ref 0. So this is standard in. This is the pipe ref 0, which is like in-memory pipe right now. And then this is standard out, or standard er, I mean. And this is the same pipe here. This is the other pipe that goes between. So this, the first pipe 0 is this pipe. The pipe 1 is this, or ref 1 is this, yeah. And then S1 is still, it's the original standard out. Hello GSVF. What's up? All right, so yeah. So okay, I think, do we have all mechanisms in that we need now for this to work? I'm just gonna fully do this example here. So I'm gonna I'm gonna have set 1 would be stream S1. We have set 2 stream S2. And do we actually need? I guess we need for standard in as well. But that, yeah, okay. Yeah, and these actually refer to the actual standard out, standard in, standard. So here we are pushing this, and then we fork set 1, which, wait, this is 1. And then standard in is the only thing we're interested in, actually. Well, actually these should just be the normal things, set different number. So we have these 3 forks that are constantly churning through these original things. We could get away of having one stream or one thread if stream was not blocking, and then we have like a loop instead. but then it's like we don't know how to check. We don't have support for checking if it ended or not. But yeah, let's just do this for now. We could change it later. So we fork those 3, and then here this would be like set 4, 5, and 6. 4, 5, and 6. I'm just trying to do a complete example here, so we have except for like process hello, I think let's just replace this with cat. And this is not sync. There we go. Now technically, actually, now when we execute, we're gonna refer to stream. Yeah, so we should have a way to get like standard out, standard in. Like exec should actually, like this is all implied that it's gonna be implied that standard in is S0, standard out is S1, standard error is S2. That's what I'm going with this. All right. Yeah. See you later, piano. Thank you for joining here. Yeah, I'm doing good. So I'm doing some IR in my scripting language. Is that the left of your scripting language? So this is Zig, which is the language that I'm developing the language in, and this is the IR, which is an intermediate representation, I think it's, which is kind of like a language in between. You would normally have a language in between your language and like the machine code, although this is not really meant to be put out into machine code. This is actually an interpreted IR, so maybe it's not an IR, but it's like so it's kind of like I'm making 2 languages at the same time. But basically this statement here would compile into these things down here. So all of this would be compiled from this pipeline here. Is the idea. So let's go through it. So we have these sets of instructions that are currently, like, they are separated. So if you run all the instructions and you end up down here and end, you don't like continue in the other sets. It's like this thing is done. So they are separate things. And here we have set 1 or 0, I mean, which is the main program. And so we push these pipes here, which refers to standard in, standard out, and standard error. So they are on the stack. These should always be on, they are always on the stack. Like they are like thread, like the stack is thread local, and it also always has these 3 things now. Because we need a consistent way to refer to standard in, standard out, standard error, and I came up with, okay, well, if it's going to be thread local and it's always going to be the same, so let's just have those as the first 3 things on the stack. And once we have it on the stack, we also fork. Actually, I should move these like this because we need to refer them here. We push these on the stack, then we fork some threads here, which will jump to different sets here, whose job is to kind of process these 3 streams. So the first set here will process standard in, so it would read from standard in and push it into this reader writer stream. So the second fork would be for standard out, so it would process anything that's like connected into standard out. It's processing that out to standard out, and then the same for standard error as well.
Okay. And then now that's like the setup of all programs. But now here's like the programs, the statements of this here. So what we need to do here is we need to spawn these processes, and we also need to create 2 pipes. And so what we first are doing is we create all the pipes here. We have 2 pipes, 1, 2. And then we fork to create the first process, which is this one. So we fork to create that one. So this is over here. Now these forks are also like, they are virtual threads as well. So everything is like, it's like inside the language itself. Still think stream is wrong. Like, I don't know what you mean when you say it's wrong. Like, in what sense is it wrong? Because it's blocking. Like you say, it's blocking. But okay, I guess we'll see. Like, I'm not sure what you mean. I'm not sure what the problem is that you're saying. But I guess we'll find out. Is this second part assembly or what? It's not really assembly, but it's closer to assembly. It's like, it's kind of like my own assembly language, but it's not really assembly. It's like a way to kind of have a flat list of instructions that you can step through, and to have to be able to kind of pause the program execution at any point in time, and then also keep the context intact so that you can resume at any point. And that allows you to not only, we can actually have a debugger that actually goes through the program step by step. So that's one good thing about that. Another thing is that I can have virtual threads more easily. So because we could have, you know, a bunch of these program contexts, which includes like the stack and, you know, potential registers and all that. We don't really have registers right now, but we could need to have it maybe if we want to be able to. We kind of have indirect maybe registers with this wait instruction here. But anyway, so those contexts could be like duplicated, and now we have 2 execution contexts. We have the main thread and a virtual thread whenever we do a fork. So that means that, well, the main thread will continue working here, but then the fork would also work here. So we can loop through all the threads and step through them as well, like step by step. And that's what's happening if you go to the evaluator. And we have like run instruction. You actually have to specify which thread do you want to run the next instruction, or run an instruction actually. And this is called from here. So we have this step function which gets the current thread and the current instruction of that thread. And if we're like out of instructions, then this returns null. So then we have an or else case to handle that. So we have no more instructions. And normally we would have like some kind of exit instruction or something. But we ran out of instructions, so we close the thread and we do this advanced thread counter, which basically is a way to kind of step through all the threads. And then we run the instructions. So basically, it's a way to kind of step through step by step. So that's why I want to have this language here. So it's okay, but it's basically to be able to have a debugger more easily, and to be able to have these threads. And why we need the threads is because we have these pipelines. I'm not sure if you're familiar with Bash, but we have the pipelines, and the reason for threads is because we want them to be streaming data from here to here, and from here to here, and from here to out, to standard out. If it wasn't streaming,
well, in this case, it wouldn't be that much of a difference. But if you call tail f, you have to have this in my language right as it is right now. So tail f server.log, let's say. This would, you know, call tail f, and the f flag makes it like kind of blocking until, well, I guess everything is blocking here, but it would make it sort of wait until, I don't know, something goes wrong with the file or something. I'm not sure actually when it exits, but it basically, it never ends. And if you want to then pipe it to something else, I'm using cat as a simple example here, but if you want to pipe it to do something else, then you can't just spawn this and wait for this to exit, because it's never going to exit. So that means if we don't have, and that's where the streaming comes in. So the streaming makes sure that, yeah, this is spawned, but we don't wait for it to exit. We actually take all the output it gives us and then pipe it into cat here. And also cat, like the output of cat also goes to standard out. So it's and that's way easier to do if you have these threads to do it. So yeah. So this language that I'm making is gonna be like Bash, but with my own, like, or not my own, but it's like it with a zig syntax. So I can show you here. Here is like MVP. So this is, on the left hand side is Runic, my language here, and on the right hand side is Bash. So yeah, you can see kind of the similarities here. So it's basically going to be a replacement. It's just that we have different syntax for some things, and then we also support some things that Bash does not support, which is, for example, floating values. I mean, I'm not sure how significant that's going to be, but it's nice to have anyway. Basically anything that Sig could potentially support, we could also potentially support with this setup that I have right here, but yeah. But yeah, so yeah, so we're trying to figure it out, how to make this come true here. How long we make it working with making languages? Not, I mean, I've mostly been doing other things. I've done some. I've written like some language stuff before, but not to this extent. Like, this is the most in-depth language that I've ever done, and I've never done this kind of IR thing before. Well, I did like a tiny assembly language at one point, but this is kind of different though. This is like interpreted, and it's made to solve like a very specific problem. But yeah, it's really interesting. It's like a really interesting problem to solve. Okay, do we have everything we need? So this would do that. We ref these, push these. This is all done here. This is simply adding these to... Actually, we don't actually need this in the thread context. We actually just need to have those instructions. No, but those we need to kind of populate the stack beforehand, I guess. Maybe you could refer to other threads now in locations. You could refer to other threads. Like this would be obviously be local, but maybe we could have thread actually, you know what if we say like ref 0 and then the fork, we actually store the fork in ref 0 in a location. That means that now we can talk about this fork. Yeah. Do we need that though? Because in the compiler we can actually, like, the fork could be, no wait, yeah, we could do that, and then wait for this, for that. Actually this would be probably here, ref 2, store this in 2, wait for 2. Yeah, we could do that. Recommendations how to learn compilers and stuff. I don't really have recommendations for that. I mean, I would, like, what I would do is just try to Google, like, how, yeah, you just try to Google, like, or search for that. I mean, it kind of depends on what you want to do. Like, do you want to build like an actual full-on compiler, or you just want to feel like dip your toes? Because there are like a couple of different like components that you need to look into for making a compiler. You know, you have the source code, of course, you have the language design, you have, and that's like the design, I guess, of the language, like the idea. And then you would have, like, you know, you would have so you have, let's say you have the source code that goes into a what's called a lexer, which, well, actually I'm gonna say tokenize. So that tokenizes, that actually makes tokens which are like more like, so the source code are, that's just a string of bytes, you know, and then you tokenize, that means that you create tokens from the bytes. So that's now you're kind of saying that now you're talking about, instead of talking about raw bytes, you're talking about things like operators, you know, plus minus, whatever, strings, numbers, things like that, just to make it more easy to parse the source code, because it's not necessary, but it's a nice step to have. And then you go through a parser which parses these tokens and creates an AST, usually like an abstract syntax tree, or, you know, it creates some kind of representation of the program here. So this is an abstract syntax tree, usually called, like, abbreviated with AST. And then you would take that AST. Now you have a choice, like, do you want to, like, you could do a lot of things with the AST. You could translate it into another language, you could compile it down to some kind of assembly or LLVM, IR, or something else. That would all then be able to create a machine code, you know, an executable. You could do what I do here, like interpret, like make an interpreted language. But yeah, these are kind of the basic building blocks to start in this end. And then let's say you want to compile to something. Let's say you compile down to, let's say you compile to assembly or something, assembly language, let's say. And then you would use some kind of a tool, like if you're not making your own assembly language, you want to use some kind of tool to do that. So maybe NASM or something to compile it down to some kind of executable. So that's the path for like a compiled fully onto executable thing. But if you just want to dip your toes there, well, it depends also on what you want to do. Like, do you want to actually make executables? Because if you want to do full-on executables, then I would also suggest you to actually study assembly, which is kind of the language that the computers actually talk in. Because that would make you learn how the computer actually kind of works, sort of. But if you don't want to start there, you could also just start at this part here to just make a syntax tree and be able to kind of print that syntax tree out so you can see your program. That's like the easier, like if you just want to start out and make something, like I think it's easier if just make an interpreted language. I read the book Writing and Interpreter in Go or something like that. Oh, well, there you go. Pun not intended. It does the lecture, AST, and all that. Okay, yeah. And then, you know, the lecture is usually pretty simple. The parser could be pretty complex though. Like if you haven't done it before. And for me, it's like I've done a bunch of parsers, but it's like every time you go back to making a new one, it's always, you know, you always have to go through this procedure to like remember how you do things and maybe try out some new patterns and all that. So yeah, so I've done these things a bunch of times, but now I'm trying to do kind of sort of, well, not really this, but more like this, like compile to some kind of IR language, and then we have an evaluator which evaluates into a bunch of side effects. So yeah. Yeah. Let's see. Do we have everything here though? Yeah, this could be a way to kind of refer to these. Kind of like this here. Setting that and wait for that. Yeah, that makes sense. And then we do need a wait destination though back. And also we need fork as a, or we need threads as a value, thread handle. Where's that instruction? And we go back. Wait for a thread to be closed. Now. Okay. Pret parser, yeah. I didn't actually know what that was until I started streaming here, because yeah, people told me about Pret parser and I looked at some code and I didn't really understand what was going on, and then I just made something kind of similar, I guess, maybe. But yeah, it works. I would say that, well, at least in my language, binary expressions has been like the main character. for a lot of things. Almost everything. Like even well, in this particular language, actually, function application is also a binary expression, which is interesting because that feels very functional to me. It's very hands-on, giving most of the code with the explanation is very nice too. Okay, cool. Yeah, but it's always the case where I feel like it's always different reading something when it's like in your mind, oh, this makes a lot of sense, and then we're trying to make it yourself. That's when you get stuck. At least that's how my experience, like when I first started out and I had this book, and it was like, yeah, it was cool reading all the code, and it like, yeah, this makes sense, but now I want to make this other thing that I made up, and I have no idea what to do. But yeah, it comes with experience, so it's not really an issue. Later you would learn that it's just a matter of experience, and at some point you kind of learn that, okay, well, now I can kind of make anything as long as I'm banging my head against the wall. Yeah, I mean, making mistakes is a natural thing that happens when you learn stuff. So, and also bugs in programs is a natural, it's just as much bugs in programs are also a natural thing that happens with code. But some people don't think that way, but there you go. Hello, Professor Logout. What's up? Welcome. What am I doing here? Right, so we have wait. Now fork. I want to say, do we always want forks to be placed somewhere? I mean, I guess maybe not. Let's make this, let's make I mean, fork could be a value. I mean, I guess it could be a value. It's just that it's also an instruction. Yeah, I guess that would make sense. It's an instruction that yields a value. And then it needs somewhere to put the result. So it's like result is going to be put into some location. Yeah. Except it's not necessarily there. Doing some performance deep dives into container builds. Okay, cool. Sounds like that could be sufficiently complex. What are you up to? I'm making a scripting language that is gonna be kind of like Bash, except with different, like with the zig-like syntax. And yeah, right now I'm working on creating this IR language. I'm currently working on pipelines to try to make them work within this language here. So I need to add a stream instruction which would streams a pipe until it is closed, blocking, which needs a location. I guess it's only gonna be like a location. Yeah. Yes, initially wanted to just formalize some of my experience-based knowledge, and suddenly I'm building Docker, Podman, build parser, and timer, and analyzer. Okay. Formalize some of my experience-based knowledge. So you're trying to write shit down? And then you're building a Docker, Podman, build parser, and timer, and analyzer. Okay. Or am I missing something there? Yeah, that's usual kind of over engineering, maybe, if I'm interpreting this correctly. That would happen sometimes. That's cool. Okay, so we got the stream. Now you see a huge issue here. Instructions in these, it shouldn't be more than 4 letters. That's a huge no-no here. So actually, they should be called no, this could just be wait. Let's just say wait. It's a wait has multiple purposes now. It's kind of I don't know. Or maybe we just say, hey, you can be called stream. Very much over engineer. I mean, yeah, but that's fun as well. And educational it could be as well. Effectively, I'm once again breaking things down to the lowest possible level, trying to get the guesswork out of build optimization. Like, I usually have a pretty good idea how to make it go faster, but now I can verify to the level I would like. Okay, not measure, verify to the level I would like to. Okay. So what kind of build are you? Like, I'm not sure. Like, why are you using, or I guess I'm having trouble understanding like what you're doing. Like, what do you mean by Docker, build, parser, timer, and analyzer? So you're trying to kind of, are you building something that you can write things down into, or what is it used for? Everything that happens during the execution of a Docker build or okay. Well, I to be honest, I'm actually not that well versed with Docker containers. Like, I know a little bit, but I've never actually worked too much with those, like building my own containers and stuff like that. But I guess it would be creating, or like a Docker build to me then means, without actually knowing, but it doesn't mean build the, like, you're kind of, it's kind of like cloning down a repo and building it from scratch basically, except of course it's in a container. So But is that what it is, or? All right. Okay, let's just have the stream. Okay, so what we do is we go to, actually I want to rename you to exec, and then we also need a type here because you need to be, you need to have a sync bool. And if we are sync, we are gonna write all sync. Actually, we could write async. Otherwise, I guess. Kind of looks a bit weird here, but whatever. All right, so that's the exec. Exec equals. So call is actually exec. So let's call this exec underscore, and then sync is a bool that we put through, and you are what? What's this? Executable call, then this is false. Well, we actually need, yeah, so this whole thing would change. This whole thing is gonna change. Yeah. I mean, I guess we could have this for like, how would this work? Okay, actually, you know what? Let's do this example. Let's do like a single instruction. So how would that work? Like echo hello. How would this be? Right? So we still have this. Okay? We don't really need this. What we basically, if we want to keep the same kind of convention here, we create a ref, we store you in 0, and then we wait for 0, and you're gonna be just that. We still have these things. You are gone. Whoops. And I mean, I guess technically we don't really need this to be in a fork. We could just say, we could just execute this directly. We could just say, you know, we could just do this and then exec sync. But that would not allow streaming though. Actually, no, we don't exec sync. What we do is we don't fork, we actually just stream as one here. No, we don't. Actually, you know what? Let's make a ref here, ref 0, and store this in 0, or we could just make a thread and exec sync. Yeah. No, we don't exec. Wait, what the hell am I doing? Yes, we do. We exec sync because the stream is already forwarded. So we exec sync. Yeah.
So we do that. So we actually do fork set for, just to stand it out. There we go. That's it, I think, because that will... No. We need to wait for it as well. So we actually need to ref, store this in 0, and wait for that. There we go. And the reason why I want it to be in sync... No, this is stupid. Why? Now we can just do this, right? I feel like I'm going around in circles here. But this should be it, right? And we don't need this set over here. Because the forwarding would happen here from the output into... We just connect... Yeah, this is just connected directly. Yeah. Yeah, so this would be that example here. We could try to make this work first, because yeah, then the exec would align with this implementation. Yeah. So let's do that. In the end, a Docker build is just a series of dependent steps that runs on code. Each step might be cached depending on what came before and what are its direct inputs, and of course there might be other layers of caching. Okay, but the idea is that you would build something from scratch in a kind of like, or well, from a container like starting point. And of course, okay, so if you have like caching, then you would use the cache if it's like sufficiently correct. Okay. So that was, it was kind of what I was thinking, I guess. I don't know, maybe. I just think like maybe like I don't know what it is, but I mean sure, containers are like good in the sense that well, the whole point is that they would have this security that they are the same everywhere. But then sometimes it feels like it feels like overkill sometimes. I don't know. It feels like sometimes, is it really necessary? But yeah, I guess it's like if you really, really want it to be exactly the same. Order of operations plays a role. Okay. Right. Yeah, but because you would have some kind of dependency tree. I mean, I actually built a kind of thing like that, like a dependency tree which had cached results, which built kind of like a web-based kind of like, you know, a builder for a web-based platform basically, which is kind of, yeah, with that kind of thing, like with caching and dependencies are can be a hassle sometimes. Containers are nice packaging mechanisms, but for sure they are not always the best. Yeah, because there's other costs that goes with it, like things. You have to work with Docker containers basically. I don't know. It's just my experience with Docker containers hasn't been the best, to be honest. I don't know. Maybe it's me. It's probably me, but it just seems like such a hassle to just make some simple thing happening. But maybe it's better for like more complex setups. I don't know. Like, because sometimes it feels like people actually like it's like overkill for some things. Like just making a project and building a project and running it. It feels like, okay, well, it's kind of overkill to have this thing in a container, I mean, sure, it's gonna ensure that it's the same everywhere, but I don't know. I would say Docker itself is one of the worst engines for running OCI compliant containers. Okay, I'm not sure what that is. I guess it's some standard for like more generic containers. Okay. Okay, so first we will go to, well, actually, okay, so let's look at this, the example here, so we can mimic this. So we're basically down here, and we are kind of already doing that. We're pushing this executable context. Well, actually, set. Set. Where's the location? Context. Location is a new ref. Oh, I see. So we don't actually push, we do a ref. Okay, I see. And then the execution actually... No, we do push it. Wait, so we create a ref and push on the stack? That seems unnecessary. We simply need to push... Wait, we simply need to push a value, actually. Yeah, we just need to push the value. So, okay. So push, and then the value is this here. So I'll remove this, go over here, copy that, put that there. Now we don't need to set. We do not need a context. There we go. All right. Basically, Docker popularized the container concept, and then standards spotted to go over open container initiative, which specifies image format, runtime APIs, etc. Docker is just one implementation of these things. Yeah. Podman being probably the most well-known alternative. Yeah, I think I've heard of Podman, but yeah, I'm not big into the container stuff. I knew that Docker was the first, but I didn't know about OCI. That's always it's always the case. There's always some standard that pops up. But it's good. Podman. All right. So could you use Docker containers, like, I guess if they are compliant, could you use them with Podman? Like, okay. So we push that, we call execute sync. That mimics this, but this isn't always what we want. We might actually have a flag in here that governs that, but it's like context dependent. It's like if we're in a pipeline, sometimes we don't want it to be synchronous. So how do we know that we're supposed to not have it synchronous is the question. Maybe we don't actually have this synchronous. I think what we need to do is kind of have to make sure that the statement is gonna take this result and wait for it. If it's waitable, maybe. So we could maybe have a waitable function here. I mean, we could technically also compile call compile expression. So and then in compile pipeline, the pipeline would actually get, like, if we would compile this first stage, we would get the result, which then would be waitable. So we wait for it because the result would be some kind of well, actually, what would fork be? Maybe it is a location, actually. Fork. No, it wouldn't be a location. Well, it's only a location if we do this. If we store it in a ref. Yeah, I guess we always create a ref for forks. Then, so that we can talk about it. So that we wait for them if we need to later. Okay. Sure. Alright, but for this one we have basically everything except for waiting here. So actually we would, yeah, okay, so actually this would actually be a ref here. So this would be a ref, and we kind of set the ref to be this value, the value that comes from exec here, which is a thread handle, which we don't well, no, it's not a thread handle, it's a process actually. Okay, maybe we do want to fork it. Set for fork it ref the fork, and then wait for that. Excuse me. The problem is, though, that this shouldn't happen. All this should not happen in an executable call. The executable call should just be this part. And we don't actually need this to wait to be sync. Okay, I'm starting to get a little bit tired here. Maybe it's time to recoup, or whatever it's called. I don't know. Because I feel like I'm close to an answer here, but like a generic answer, but feels like I'm going a little bit too much back and forth here, and I'm running out of brain juice. So yeah, I totally lost the thread here. Because the problem is that, like, when we call executable, we probably want to do something like this. We probably want to do this async, right? I'm trying to solve the puzzle basically. So we do this async. The problem here is that this thread is going to exit. Wait a minute. If it exits, it should wait for the process to... Right, if we always have a process connected to the thread... Oh, wait, aren't we doing that already? Maybe not. I think we do it in the evaluator. Right, because in the evaluator, okay. Yeah, the evaluator automatically spawns the thread and it connects it to the process ID, but that's not what we want to do. We could potentially, like, every time we exec, we actually, that actually is like the original, it's like the exec of the actual operating system is like, we're calling exec, that makes the thread, that takes over the thread to be the new process. We could do kind of the same thing here. Like every time we call exec, it's gonna change the thread's process to be that thread. We just have to make sure that we always create a thread when we spawn a process. So we always have to fork when we do this. So actually, the executable call could actually always create a fork. Yeah, okay, so it always creates a fork, and we can potentially, we also can store in the ref, and we can also, but like, essentially this wait would be optional. It would depend on the context. Like if we only have one statement like this, we would have the wait. If we had a pipeline, we don't wait. We do the pipeline instead. But if we only have an executable call in one statement, we do the waiting. Yeah. We basically look at the results of what we get back from the executable compilation, which would be this ref here. And we check, okay, is this waitable? In that case, we wait on it. Yeah. Okay. And now this doesn't really need to be sync or anything, so we can actually, we don't really actually need sync. I guess we could keep it, but it should always be false. Okay, so what we need to do is we need to create a ref for, oh my god, what's going on? We need to create a ref for the thread ref, for the thread. So this is going to be new ref, and the name is going to be exec thread
something like that. Now we have that thread, and then we're also gonna fork, which we don't have yet. So, but we're gonna fork, and we're going to. Actually, we need a new. We actually need a new instruction set. So this is gonna be exec instruction set. It's gonna be instruction. What's happening? Add instruction set. Yeah, that's an instruction set. And then we fork into that set. And we also have the ref, so exec ref. Okay. What else? We have standard in, standard out, standard er, which are just stack 0, stack 1, stack 2. So these are locations. Yeah, it's just gonna be stack 0, stack 1, stack 2. How do we create that? I think it's like in instruction we have, no, not instruction, value, we have adder. Oops. No, wait, location, location, there we go. Stack is just a number like this, stack. Do we have a convenience thing here? No. Alright, so where are we? Here. So stack, so this would be stack 0. Stack 1. Actually, you know what? I'm gonna make convenience for this. So this is gonna be like stack or thread standard in, which is gonna be a location. This is going to be stack 0. Actually, we don't need self, but whatever. Thread standard out. Standard 2, 1. There we go. All right, those are the locations, and now we can just refer to them here. So thread standard in, thread standard out, thread standard. There we go. And of course we don't have, oh wait, thread, yeah, okay, thread ref, whatever. So now we need a fork function. Which is here somewhere. Let's add this fork. Yeah, I guess it's a void. Maybe. Yeah. So source thread ref, so this would be results is a optional location. Then we have instruction set, And then we have the standard in, which is the location, standard out, and standard er. And this would simply do this, except we're dealing with a fork instruction. I mean, actually, the instruction set is wrong. This is actually going to be like a location. We could potentially fork into anything. I mean, usually I think probably wanna be at the beginning of an instruction set. So whatever. Let's just have it like this. But we do need this fork function here, though. Fork, which is also gonna take all these things. Whoops. And this is a fork. Destination, wait, yeah, standard in, standard out, standard er. Okay. Oh, this is actually address, okay. Wait, yeah, destination is address, okay. Destination, yeah, fine. Instruction address. And right, so this would be exec instruction set 0, right? Oh, init absolute. There we go. 0. All right. Cool. So now we're creating the fork, and let's look at the code here. So where are we? We created the ref. That's over here. We're forking, which is this one. So we're forking with the ref. We are selecting the new set that we created, and then we are passing the thread local standard in, standard out, standard error. And then we wait for it, but we don't do it in here. What we do is we want to have these push and exec. However, they need to be compiled now in the new set. So what we do is we say current instruction set is equal to exec instruction set. So now that changes that context, and then we set it back to whatever it was before. So we have to store that previous instruction set, and we set it back to whatever it was before, and then we continue. There we go. All right, now the push should be the same thing. And exec is also the same, and that's fine. Okay, but this is wrong now, so this needs to be the ref here actually. So this is the thread ref. There we go. So we're returning that because later we want to be able to wait for it if this is the only statement here. There we go. And I think it's like compile statement. Now, maybe it's not compile statement. Actually, we have a separate, like if we have an expression at this point, do we want to be able to kind of talk about it as being like, now actually let's do results is this, okay, try course, okay, that's the result. Now I'm gonna say like if self is, or if is waitable results, then we wait on it. So then we actually do wait, or yeah, wait result of value. So now we need the wait function, fork wait. Oh yeah, I need the source. The value is, no, the waitee is a value. No, it's a location actually. Yeah, it is a location, okay. And then this would be error void, turn self and instruction init from source wait waitee. Okay. We don't have is waitable. So we simply return switch result value, and we have a bunch of cases where it's waitable or not. So we're waiting on threads. I think, yeah, we're only waiting on threads, I think. So it's gonna be like a ref. We don't actually know the value here though, I don't think. We don't know what the value is. Yeah, because it's like in the... Yeah, because the thread is created in the instructions world, in like this language IR world. So we wouldn't know the handle until we run the evaluate the thing. So we wouldn't actually know what this result is because we don't have like type checking here. But I guess it has to be a location. So it has to be a location. Then I guess it's true, otherwise it's false. And location is actually an address, though. Okay, sure. Oh yeah, so this is a value. No wait, this is a result. But we know it's it even says the function should exist. It's not a function. Is this because I'm using try? What? Oh. Whoops. Hang on. How can we solve this here without having to type result here? I mean, this would solve the issue here. But it's annoying. I don't want to have to do that. Okay, whatever. You know what? Whatever. I was just trying to like, okay, could we figure out what is the pattern? What is the correct pattern here? But member function expected to organize. You want the source, right? Yeah. Source is the statement. Yeah, you are safe. Yes. And you're actually not a location. From location, we don't have two location. Yeah. We have from, wait. From adder. Yeah. So we do have from adder. There we go. Wait. Oh, the value. Oh. Wait, but you have. Oh, the data has from adder to adder. But where's map adder though? Context. God damn it. So this result is actually, well, it's a value. It's turned into, so we compile it. So we compile, no wait, from location creates two, like it takes two adder here. What? This can't work. Now I am confused. No, it does work because the address is actually. No, okay. Yeah, it does work. Sorry. I thought adder was like 0, but it wasn't. It's not. From adder to adder. Now we need to get it back, unless we say that the wait instruction actually takes just an address instead. The waitee is not a location, it's an address. But that doesn't make, no, that doesn't make sense. Why is this different? It's because the location is like coming from a runtime value now. Yeah, I guess it's different then. It's like a runtime thing. Because we compile, no, yeah. We have to be able to create a location out of this. Where else are we doing that? In the if thing. We have result in a ref that we could potentially bind to something, for example. So bind, compile binding declares a thing with the result. Okay. No, it should be fine. But we need to kind of map the, we need to, or wait, no, okay, whatever. Let's just do wait is, this is an address instead. I think all instructions actually have to have this now because we can have runtime locations. So these locations are like, they are like compile time known, but because a ref, oh no. Like, I don't want to have a discrepancy here, but I guess we'll have one. There we go. No, okay, I'm going back and forth, but it's basically, I'm reminding myself on how this works. So the locations are like resolved addresses, basically. An address is actually just a number. It's an address in the usize space. So it's a you know, from 0 to whatever is up there. And then we can turn it into a location, which is kind of like a resolved address or a more descriptive address. So this could be either a ref, it could be a you know, scope. Okay, it could be a stack. On the stack, it could be an instruction address, I guess. Well, that doesn't really make sense. You can't map to an instruction address, but you can map to, or the read-only data, to a data or stack or ref. Actually, what is the address of the ref? It's the, okay. Okay. I'm gonna say this. I'm gonna always assume that this is an address. Or a ref, I mean. We're always assuming it's a ref because The only thing we wait for are threads, and the only way to store a thread is in a ref. Sort of. So we're gonna do this here. I'm not gonna add a comment. Okay. Cool. So now you are the waitee. You're a actually. Oh, we don't have this. Wait is waitee location. There we go. Right. Okay, actually we could actually say get. We could have a get. No. We don't actually. We don't actually store these names. Okay, so the ref is actually lost then, so let's what is this actually? This is just a name and an address, so the address is there and then the name is like we don't actually know what the name is. I'm just gonna say it's like unknown. It's some kind of thread. Yo, piano. Yeah. It's 11:30. So I'm gonna give up here pretty soon. I just wanna finish off there a little bit here. Why is this an issue now? List the returns. Oh yeah, we need to return this. There we go. And from location. There we go. And you are a location. There we go. Awesome. Okay. Now, compile executable call. So this does that. New ref forking. We are creating a new instruction set. We are changing to the new set. Now we're pushing these things. The executable call context, and we call. And we execute, and then we restore the set. We return location of the thread ref. This is then gonna come back to the compile statement, which then checks, okay, whatever we get back from here, is it waitable? Then we wait on it, and that should be good. So I'm gonna make IR2 here actually. IR2, which is just gonna be echo hello. Now, one thing that we're missing as well, okay, one second, is the other things. It's this part here. So we're kind of missing this part. So
let's go to this part, compile initial. Now, before we had these as refs, I'm gonna delete this. We still want to have these pipes though, but we're simply gonna push them now. So we're gonna push these values. You don't have a source, and then we have the value, which we don't have a ref now. There we go. So those are the values. So remove that. Oh, I see. Yeah, I'm not that hardcore. Yeah, if I stay up that late, I will be very tired next day. Okay, so now we've done... God damn it. These things, we're pushing that. We don't do the forks though. We don't actually have the forks, but we do. So what we need to do is we need to create these sets as well. So we have standard in set is gonna be try self add set. We have standard out set and standard set. So now we have these sets, but we also need to like create them as well. So let's have like the previous instruction set, and then current instruction set is equal to previous instruction set at the end. So now let's do the first one. So let's do this is equal to standard in now, and then we'll do self stream, and then stack 0, which is going to be standard in thread, standard in. Right, so that is that, and then standard out set is going to be thread standard out, standard it's going to be thread standard there we go. So now we have these 3 sets. We restore the set at the end. We don't have the forks though, so we have to create the forks now. So fork source is null, result we don't care about the result. The destination is standard in set. Standard in is thread standard in, thread standard out, thread standard there we go. And then we have 2 more of those where this is standard out set and this is standard set. So there we go. Now we have these forks as well. So we have, this is like the initial compilation that happens. We get these sets, we add these instructions here. We need to add this stream instruction as well. So let's do that. Stream. And I guess we need source and we need streamy. I don't know what to call it. And then this is a location. And there we go. I don't think we actually have this here. No. So stream is, oh, it's just a location though. Okay, okay. So it's like, well, yeah, we need it here though. So this is the streamy. It gets the correct term. There we go. Oh yeah, the source is null, of course. Oops. Alright, good luck. Or thank you, I mean, have a nice sleep. Instruction errors by use size. What? Oh, wait. Oh yeah, the instruction address, right. So this would be init absolute standard in set 0. No. Standard out set 0. Standard set 0. Okay. Now what do we have here? Stream local constant shadows declaration of stream. Right. Let's. What is this actually? String literal. I'm gonna call this the S stream, maybe. S underscore stream. Sure. That's a new way of making up a random identifier for me. Okay. So yeah, I think we should have the instructions ready now. But we don't, like, the evaluator doesn't know what to do here, but we do. The compilation should be good. We should be able to see the output. So let's go over here. Let's do the thing here, and of course it's gonna be an issue, but here you can see we're pushing a bunch of pipes. We're forking those into set 1, 2, 3. This is set 0. Set 1 is we have the stream. Set 2 stream. Set 3 stream. We don't see the. I guess we don't see the location of the stream. But yeah, it's there. And then we have set 4, which creates the executable context here, and then we execute that, and then it's trying to run this, but then we encounter fork, which is not implemented, so we have to do that. But I think the basic structure is here. Everything seems to be going good. Here we have the exec thread ref, which we it actually says like unknown thread here. It should actually be, well, we do see the address as well, I guess. Yeah. I mean, yeah. It's not great that we kind of lose the name. We could store it somewhere. Maybe, and that will solve the issue. But anyway, we see that the address is the same. And then we fork to there. Yeah, cool. So so we need to do the evaluator for this. So here we got all the different things. Now for the exec, we actually need to change a few things. Right, so here we're popping the stack, we're resolving some value, we are getting argv here. Yeah, all of this is just building the argv. And then this one is, I think that's the old way of doing it, which was way easier, but anyway. And then we spawn the thing. And here's where we don't do this. Here we automatically create a thread for the child thread. We create a context, or we get the context and we set some things there. So this is not what we're doing actually. We don't do any of this. Yeah, because now we have the fork instruction, which we have somewhere. Well, we don't have it actually. We need to create it, so we need a fork. Okay, and on the fork we have a bunch of stuff. We have where we should end up, where we should store eventual information about the thread. We have standard in, standard out that we need to push into the thread context. So we are going to say context spawn thread. So we got our thread here, and now we need to set well, that's the thread. This is like the thread handle actually. And then we need a thread actual information is on the context of thread handle. So there we go. Now we have that, except we don't, or we do, or we don't. We should have it. I'm gonna unwrap this because we should have it. Right, so now we get the thread context. Now we are going to say we're going to say I want to get like the main thread. Actually, no. Well, okay, this is the spawned thread. We already have a thread in the thing. This should be like new thread. New thread. New thread handle, new thread. There we go. And then a new thread. Hang on. First off, we have the old thread. You're gonna have a ref set. No. Is there a way to kind of set the ref, or no? Maybe not. So this would be like items. Whoops. Where do you? It's like get or put. Refs put. No, it's get or put. Yeah. That does that set actually does this, which we need to do. So we get the thread pointer, and I guess we only do this if we have it. So this would be the result. This would be the ref that we need to store it in. So we get the pointer of, actually this is a location. Now it has to be a ref. It's always a ref. So that's, so this is the location ref address. Yeah. Ref not found. Yeah, and then we set that ref to be
some value, and the value is going to be a thread. Which is the new thread handle. So that's the value we set that to. And now we actually need to have a new value type for that, which is cool. Let's have a thread value type, which is just a usize. And we can add this here. What else do we need to do? Deserialize. I mean, I guess it's the same thing here. Serialize. Sure. Format. Thread. I mean, we have the ID here, so we could actually put the ID here. There we go. Okay, we have a bunch of places now. Well, okay, so material is string, I guess a thread. I mean, actually a thread could become, because it has like standard out. But okay, I'm not thinking about that right now. And new thread. Thread, no member name thread. Oh, excuse me. No, it doesn't have thread. Well, I guess we could just say thread equals that. There we go. Okay. So now that is stored in the result if we have one. Okay. So next up is what? I lost myself again here. We got new thread. Oh yeah. So we need to store standard in, standard out, standard error in the stack now. So we actually need to add some stuff to the stack here. Like, yeah. Now the stack. Yeah, let's just allocate it. And then the item is going to be the pipe or the location of the pipe. No, it's just going to be the pipe. Yeah. And so we have standard in, which is location. So actually we need to like resolve this. Which gives us not the address, but the value. Thread is our thread, value is from location. Pretty sure, or not, maybe. We could also say to adder here, and then from adder. So right, okay, now it's saying like if this error here is
not in the error list, so we have to add it. So this would be adder, wait, no, location. Yeah, there we go. And I guess this is a try as well. Alright, there we go. Try there as well. Okay, now we need to do this for all the different things. So this will be standard out, and this will be standard out. So now we're priming up, kind of like passing these as arguments to the thread. So this is like creating the stack things. So the first item in the stack is going to be standard in, second is standard out, third is standard. So yeah, good. Now we also return continue, so that we can continue execution here. Alright, so that's what's happening with the fork. We spawn a thread, we mess with the thread context, we if we're supposed to store the location somewhere, we store it, we store the thread handle there, and then we continue, and we push the stack there, and then we continue. So that's all we're doing with the fork. Actually, what the hell? Also, what we need to do is we need to actually set the instruction counter to be well, isn't that just, it's gonna be this, but we also need to resolve it as well. So resolve address. Yeah, all right, there we go. So we're setting the instruction counter, we're priming it up with the stack stuff, and we're storing the handle somewhere. Okay, I think that's it, right? We don't have anything else to consume here, so all right. Compile calling value. Oh yeah, the thread. There we go. Okay, now we also have wait. So wait. What do we do with wait? We have a waitee, which needs to be resolved. So this would be resolved to some kind of value. All right. Wait. Why did that happen? All right. So now we got the value. Now the value has to be some kind of waitable thing. Otherwise, there's going to be some embarrassing errors here. But basically, we switch on waitee, and it has to be a thread. If it's not a thread, we're gonna have some errors here. So yeah, there's gonna be like error. I'm just gonna say unsupported instruction for now. Actually, let's add unsupported waitee. to be clear on what's happening here. Alright, so we got the thread, we need it, so this is the thread handle that we get. Out. Alright, we got the thread handle. Now, how do we actually wait for this here? Is the question. Well, this is gonna be like a blocking thing. No, wait. It's actually pretty simple because the thread has a wait function, and we simply wait for the thread handle, which just this is just gonna set the waiting for thing. So it's just gonna change the context for the thread to wait for the thing, and then the evaluator is gonna handle that later. So this is we're just setting that, and then we return continue. Okay. So that's wait, except it's not. Oh, I see. I need to do this whole dance here. But this is wait. Dot waiting. All right. Okay, no more compilers. We have the wait instruction, which I think should work. Not sure if we fully implemented wait on the other end of this. We have the fork instruction that should work now as well. We're spawning up a virtual thread. We're hooking everything up. Yeah. So I think now it's like it's gonna be hard to see what's going on if we just spawn this up. But I think we could also try the debugger. But let's just see what this will end up with. Okay, we end up with some kind of error here. So let's see. We have, yeah, this should all be the same thing. Oh yeah, we don't have the stream instruction. We don't have. That's right. But okay, let's see what's going on here. So we're starting to evaluate some stuff. We're doing the fork, and then we get an integer overflow directly. Okay. Right. Integer overflow, interesting. Wait, where was that happening? 255 context. Okay. So you are a U size, you are a U size, and you're not. Well, you're taking the the max int. How do we get an overflow here? Actually, isn't this wrong? Shouldn't this be plus? This should be plus address, right?
Hello, common bit. Do you not mind all the dot braces in the code? I don't actually. I kind of, and it was kind of annoying at the start, but now I've gotten used to it. So it also, I mean, sometimes it's nice because it differentiates blocks from struct literal. So it does have its purpose. Shouldn't that be plus address? Because address... No, wait. Address represents the absolute address, right? And here is like if we're creating a stack. Oh, yeah. Now I see. It's more than or equal to stack. That's why we get an overflow here, because we're subtracting a number that's larger than this, which ends up in a... Of course, it ends up in a negative number. And that doesn't work because this is an unsigned integer. So what we need to do is we need to say the other way around, I think. Because then if address is equal to stack, it should refer to this first item on the stack. If it's equal to +1, that means number 1, and so on. Yeah. Okay. I've actually, that's interesting. I think it's weird. We should have been using the stack before and it worked, but okay. Maybe I changed something. Okay, what? Yeah, so this is probably due to not having stream. Yeah, stream is not supported, so we haven't done the stream yet. Now we did do the fork, so that's nice, but we haven't done the stream, so I forgot about that. So let's go here and see if we can make the stream come true. Stream. All right, what are you up to here? So we have a bunch of different things. Wait, what's happening here? Location. All right. Yeah. Okay, it's kind of weird that this is actually an instruction. I guess what we could do is we could forward the stream. Yeah. We'll resolve the location. Streamy. Okay, that's the value. And it has to be a pipe. If it's not a pipe, then we have a problem. Unsupported stream E. And then yeah, so we call forward. I guess it's unlimited. I'm not sure actually if we should limit. Maybe we should limit it because of priorities. I don't know. And then we can get some. This would. We could get a stream error. We could also get. What is the stream error actually? Oh, it's just a reader stream error. Okay. But the end of stream is not
part of that. This is... So, should we just do try here? Let's just do try. Okay. And then we switch. Switch on that. Now this could be a number of things, which is no source, closed or not done. So not done, we simply return continue. If, actually, we do return continue. However, we don't want to advance the instruction counter. And the instruction counter is actually automatically advanced in everything. So we actually need to we need to decrease the instruction counter. Except we can't because it's 0. Okay, maybe we should have a separate thing here. Continue. What would that be called? Like block? Or continue no instruction adder increase? Or counter? I don't know. So if we're not done, we don't want to. We do want to continue, but we don't want to increase the counter. Okay, and then we have something here. It's like if we get this, then where is that happening actually? Continue. Actually, maybe it wasn't here. Maybe it does happen in here. Ah, there we go. Oh, I see. It should be happening in here then. There we go. So, right. So continue. We do this. But if we don't want to do that, then we do that. Okay, cool. Now we can kind of, yeah, we can do that. Cool. And also, same is true for the jump. Because here we're kind of decreasing the destination address by 1, which could be bad because we're jumping to, we could jump to address 0, and then this would be an overflow. So this is better now. So we can do this, and we don't want to increase the thing. And if we set this, we don't want to increase that. There we go. Yeah, and you're complaining about return values here. So actually, let's just return directly here. And you can be a thing there, stash, there we go. All right, so now we have to
return things here. If we don't have a source, it doesn't really matter. But it basically means that it's not set up correctly, which I just remember we don't actually do as well. We have to set up the original things, but that's basically gonna continue, no instruction counter. This is gonna continue, except no, it is gonna, this is just gonna continue. So we can't. This means that we're kind of blocking. If we're not done, we're blocking. If we have no source, we're blocking. If we're close, that's the only way to continue from this stream here. So there we go. Now we've implemented a blocking thing. It's like these things, like it's like you've at the start you feel like, okay, well, this is gonna be hard, like to do a blocking instruction. But it's like, well, we just don't increase the counter. And there you go. There's the blocking. There's the blocking instruction. So, and yeah. So there you go. Now, what's happening here? Alright, we're gonna make no distinction there. Same thing here. Okay, cool. Alright, so we are missing the thing where we need to actually set up these pipes. So I'm not sure if we want to do it like in the compiler though. Maybe we have to. Do we have standard in and all that here? No. I mean, we could have a setup function here which like connects them, which would take, I guess it would have to look at, no, we wouldn't have it yet. Wait, this is kind of weird as well. Like, we're creating the value, like, so the whole language is like compiled in memory, right? So like what I was thinking, like things that's created in the compiler, like all, like the value of the pipe is actually like a pointer that points to a reader-writer stream, which is not really serializable. So you couldn't actually write this program as a source code and then compile it that way right now. I mean, we could make it like that later, but right now you couldn't do that because of the value type is not serializable. So what was I thinking here? Yeah, this is kind of weird. Like we kind of do need to be able to, like, let's say we kind of do need to connect these pipes like from an instruction actually, which yeah. I mean, yeah, so let's say we have forward standard in, let's say, and this would have a location for us. And what we would do is we would resolve this location. What a value. Yeah, we resolve the location. Whoops. I think you were a try. So there we go. Now I have the value. And then we switch on that. You have to be of height. Else. Unsupported. Forward. You are a pipe, so what we do is we say pipe. Now we're forwarding standard in, so that means that the source, I think we need to connect the source to standard in here. Where is the thing actually? Where do we have this stuff? I guess we just add it in the config or something. So standard in is a reader. Standard out. No, actually it's a closable reader. No, wait, these are... Yeah, no, yeah, no, yeah, no, yeah, no, yeah. Yeah. And then this is a closable writer. There we go. Alright. So then this would be config standard in. Yeah. So we're reading from that. Oh, it's an exit code. What? Oh. Right. Exit code. So this is like, yeah. Right. And then we return, continue. Okay. So we need like one of these for each one. I guess we could have one instruction for all three. Forward standard, which would have the thing, and this would be for standard in. I mean, we still need to do it for all three. But at least we only need one instruction, I guess. Now this would be destination function instead. There we go. Yeah. And standard error. It's kind of weird with this super special instruction, but whatever. Okay, so now we need to create this instruction here. I'll just put this here. Forward. Program standard in, standard out, standard error. Forward standard. Alright. I need to stop being childish. Okay. Let's see. Source. What the hell? Okay. Forward standard. No. It's a constant struct. Standard in is a location. Yes. Standard out. Standard. I mean, they are actually always going to be the same, to be fair. So we don't actually need them to be... Yeah, okay, we don't actually need them to be... We don't actually need anything. We just... Yeah, we know standard in, standard error, because it needs to be available at all times. So actually, we don't actually need to do this. What we could do here is say from address, and this would be wait, what are you actually doing here? Am I doing this the whole wrong way? Yeah. So actually, this is a yeah, it's an address. From address. Yeah. Now, okay. So let's do like location. And stack 0. So that would be standard in. And then we do to address. Right? Okay, standard in stack or address. It's going to be location stack 0. So that's the address. Standard out is 1. The standard error is 2. Now this would be like well, we can resolve this, and we'll say standard in to address. Try. There we go. So that's standard in, standard out, standard error. The usual suspects. Standard out. And this. Okay, so that's our things, and then I guess, I mean, okay, I guess we still have to do this crap here. Okay, fine, but now we don't need to pass anything into the instruction. We can actually, we just refer to the first 3 items of the stack. At least that's what we get from that. Alright, yeah, now we need to pass in the things to the thing. We need to create those closable things. Well, we actually have those in, we have them in the runner. Or the run script, I mean, so we do have them here somewhere. Well, we have them as writers. Where do we create the things? Over here? Yeah, okay, so we need to move this over here, of course. This is connected, yes. So actually, this is kind of weird because these are actually another step in between, I think. And so, wait, or are they actually? Maybe they're not, actually. Well, it's wrapped, but it's wrapped from the writer. Now this is that's the actual standard out. It's just wrapped by a tracer, so we can trace it if we want. And then we write, yeah, this closable right is that direct. Yeah, okay. The only thing we don't have is the standard in. We don't have the standard in, so that's a bummer. 1 second. So, okay. Wait, what am I doing? I need to move this out here. Right, because now we can actually pass in these closable writers here. Okay. Wait. Yeah. You know, yeah, let's just add standard in, so this is fully completed here. Where's the other one? Here. You have a config. You don't actually have like
the things in there. I'll just add this here. Standard in. There we go. So now you need standard in closable reader. Alright, now these things need to go in here. Can you disappear, please? Thank you. And what's this? Alright. Right, because we don't have standard in closable reader. So we need to create standard in closable reader. Your closable reader. And we need some kind of reader here, which we don't really have. But I'm gonna create like a stub reader. So stub standard in reader. And we actually need a closable as well. So standard in closable. It's gonna be never closes as well. I'm gonna sleep. Don't worry. You need to sleep. Man, I just wanna connect these things and then I'll go, I promise. Alright, so we need this stub standard in reader. Now where are we gonna get this? So there's like standard in reader. I mean, you could do fixed with an empty buffer. So that could be the reader. So that would be like standard in stub standard in reader. That's a perfectly good reader. Alright. And there's no field named. Oh yeah, these are called these things. There we go. And run needs why couldn't we could just add the config here. Oh, we have the config. Self config. Standard out. Standard out. Standard. Alright. Not sure why these are like different. These are different configs, but whatever. Alright, now you have like a different error, stream error. Wait, this stream error is... Oh, it's actually from stream, okay. So it's not this stream error, it's gonna be runic stream error. There we go. No error named unsupported forward. Fine, let's add it. Okay, there we go. Kind of forgot. If we did something that should work now or not. Okay, I think Vim froze here. Do you go to the gym? No, not no. I did some running for a while, but I stopped for an unknown reason. I did also like combine running with outdoors gyms, but yeah, I should pick up on that. It's very good for the body and the mind. But yeah, god damn it. Okay, well, this is gonna be it for this time. We're stuck here. I think what happens is that it probably outputted a whole bunch of stuff, probably, and I pressed interrupt, which probably causes Vim to kind of gather everything here and trying to display it, which sometimes can take a while. But yeah, I don't know, we'll see in the morning. Yeah, but that's gonna be it for this time. So thank you very much for joining me here, and I'll see you later. Bye bye.